So if you have a concave utility function, so let me draw the utility function. This is a concave utility function u. If the function is concave, then, and that was the idea of the quiz question on Toledo, if you have a concave utility function, then you prefer to, to have certainty. You avoid variability. So in the question, there were two losses, x and y. They were very simple losses. You could lose or you could gain $2, or the y random variable you could gain or lose $20. Right? So on average, you get the same, 0, because it's equal probability, but just the y is more variable. If you win, you get more. If you lose more variability. And if you are a concave decision maker, you prefer the risk with the lowest variability. Yeah? Although the y random variable you can gain 10 times more compared to x, that doesn't really influences your choice. You are more looking at the downside. You can also lose much more, and you are afraid mainly of that. That's concavity. Convexity. A convex utility function is a utility function that, for example, looks like this. A convex function. In a convex utility function, and that's again in the quiz question, you saw that the decision maker prefers the risk with the highest variability, because a convex decision maker is looking at the upside, right? The convex decision maker mainly sees that for a random variable y, you can gain 10 times more in the positive scenarios compared to the random variable x, and therefore you want to get x, right? While the downside, that you can also lose 10 times more, is not that important for the convex utility function, right? So concavity means you avoid risk, you avoid variability. A convex utility function means that you want to take on risk, you want to take on variability. The more variability, the better for you. Yeah? Convexity, concavity. And in that sense, let me first clear here. Okay. In that sense, convexity models a risk-loving decision maker, right? Concavity was a risk-averse decision maker. Convexity means a risk-loving. This is risk-averse. This is risk-loving. And when you talk about variability, a concave decision maker does not like variability, whereas a convex decision maker loves variability, right? Okay, convexity, concavity. And then there was a situation where we had a risk neutral decision maker. What means risk neutral? It means that your utility function is this linear function. And assume that I have a utility function that is linear, and I have two risks, x and y, with equal expectations. Again, that's the question in the quiz. Then if you look at the expected utility, so the expectation you own w, and you're facing, for example, the loss x, so you subtract x, then I can write this as the expectation as a times w minus x plus b. Right? If you use the linearity of your expectation, you get a times the expectation w minus x plus b. And then you see that if you have a linear utility function, your decision or your expect utility is mainly driven by the expectation of your random variable. Remember that we had the St. Petersburg paradox, where we started with a gambling game, saying, well, what do you what are you willing to pay for this game? It's not a lot, whereas the expectation is plus infinity. Conclusion was expectations are not a good way to value, to make decisions in this case, unless your utility function is a linear function. A decision maker with a linear utility function is using the expectation to make decisions. Meaning that if you have two losses with equal expectation, then the expect utility of suffering loss x is the same as the expect utility after suffering a loss y. You are indifferent between losses with the same expectation, although they have different variability, right? So that's concave, convex, linear. Okay, and the effects of variability. All right. Um, in order to quantify or to measure the risk averseness of a decision maker, you are looking at how concave this function is, right? The slope of your concave function tells you a bit on how fast your utility is going down when you are losing money. And of course, the steeper your function is, right? The steeper your function is, it means that from the moment you are starting to lose money, you are very quickly decreasing your utility, meaning that you want to avoid that, right? So the steepness of your utility function, the second derivative, is a measure of how risk averse a decision maker is. And then there are several measures for risk aversion. And one possible measure is that Arrow-Pratt measure of absolute risk aversion. So it's defined as follows. So the measure Rx is, you look at the second derivative, right? The second derivative, which when you are concave, it's negative. That's why you put a minus. It becomes something positive, and you divide it by the first derivative. And so this is just a definition. In the exercises, you find a way to find a good interpretation of what this risk aversion means. I think it's the first exercise of the exercise sheet. So if you want to understand or get some more intuition on this measure of risk aversion, have a look at the exercises. By the way, for the exercises, I think, and I will check after the lecture, the exercises are already there, so you can start having a look at the exercises, trying the exercises a bit. I will upload solutions of the exercises, except for the exam questions, but for the rest, you will have solutions for, I think, almost all exercises, but I will only post them at a later moment in order to force you to really try these exercises yourself, right? And I think it's, probably I already said this in the beginning, but it's very important that you try to make the exercise yourself. The exam will be based on exercises and the interpretation. So most exam questions will be like, you have here a certain situation, prove something, calculate something. So that's like very typical exercise that you also have in the exercise sheets. And then there will be some interpretation. I will ask you to, can you explain why, if you calculate the formula, why this thing is going up or going down, or what is the interpretation of the parameters involved in this equation, and so on, right? So it will be a bit calculation and then interpretation. That will be, I think, most of the exercise. So you get like 4 or 5 exercises depending on how many sub-questions I have per exercise. And for that, it's really important that you understand that you understand how to do an exercise, right? Just understanding the solution of the exercise will not be sufficient. You really have to go through the pain of trying, finding a solution, trying something else, and so on. All right. So that's on the exercise, and the exercises are there. So have a look at it. Try the exercise. If you have questions, just ask me or the TA. Okay. let's now have a look at the relation between, whoops, expected utilities, what we explained so far, and premium calculation when you want to take insurance. And there are two sides when you want to take insurance. On one hand, there is an individual, or also the insured, or at least the person that is looking for insurance. So this person is facing a loss X which is positive. Could be your car, right? You want to insure your car and you know that maybe I will not have any accident in the next year, then my loss is zero. Or if there will be an accident, I will have a positive loss. I don't know exactly what amount I will claim during that year, so that's the random variable X. And this decision maker has a utility function U to assign utilities to each level of wealth. And initially, before you decide on taking insurance or not taking insurance, you are holding a wealth W, right? That's the insured, the individual. And the individual will try to figure out, should I take insurance or should I not take insurance? Yeah, where here, for the moment, we assume that we can say, well, we insure the full risk or we not insure at all. Of course, you can make variations on this situation where you say, well, should I insure, say, 50% of my loss or should I insure everything? Right? That's more or less the same problem, slightly more complicated, and you can do that yourself. But we looking at the situation where the insured, the individual, has to decide, I take insurance, full coverage, or no coverage at all. And what is the optimal, the best choice? It's the one that gives you the highest expected utility. So that's the viewpoint of the individual. On the other side, there is an insurer. And if the individual, after doing all kinds of calculations, decides I want to take insurance, then the other side, the insurer, has to decide, do I accept this risk, yes or no? Because maybe for me this risk is too dangerous and I prefer not to insure. So also the insurer is having a decision-making problem. Should I accept this risk from this individual in return for a premium, or should I not insure it at all? Right? And if both parties, individual and insurer, decide that for a given premium, it is best to the individual take the insurance, the insurer accept the risk, then they can do business. Then they can say, well, let's sign this insurance contract. But if there, maybe for the individual, it's optimal to take insurance, but for the insurer, it's not optimal to accept the risk because maybe the risk is too dangerous. Right? So there are two decision-making problems. We will solve first the individual, then the decision maker, and then we will see what are conditions that has to be satisfied in order to have a feasible contract. A contract where both parties are happy. That's what we try to do. Okay, and for the insurer, I also have a utility function and initial wealth. But now I use the capital letters because the insurer can have a different utility function than the individual. The insurer has a different initial wealth than the individual. Right? So you are solving the two problems with different utility functions. Okay? Clear for everyone so far? Let's have a look at the viewpoint of the individual. So the individual, let me draw it here. This is our individual, and this individual is facing a risk X. That's your risk. It's a loss, meaning that if you suffer the loss X, we have to subtract that from an initial wealth. So the individual has two choices. the individual can decide to not take any insurance. In that case, you are having an initial wealth W, that's the amount of money the individual has, and you have no insurance, meaning that you are liable for any losses. Meaning that if you suffer the loss X, you have to subtract X from your wealth. After suffering the loss X, your wealth drops from W to W minus X. And the utility you will reach is U W minus X. And X is a random variable. You don't know what exactly X will be. Can be 0, can be very large. So utility that you will reach after suffering the loss X is also random. So we take an expectation. We look at this expected utility. So this here is the utility of the individual after suffering the loss X. Right? What you expect to get for utility after you suffer the loss X. In case you take insurance, if you take insurance, it means that you have, initially you have W, that's your amount, but if you sign your insurance contract, you have to pay a premium. The insurer will say your policy will be in force from the moment you pay the premium. Then you get the coverage. So you have to pay the premium, meaning that the premium is subtracted from your wealth. Your wealth drops from W to W minus P. You pay the premium, but after you pay the premium, there are no liabilities for you anymore. Because whatever X is, if X is 0, if X is 100 or very large, the insurance company will cover that loss. So it's not your loss anymore. So it means that after suffering the loss X, your wealth stays at W minus P, right? So the utility is the utility function you applied on W minus P, but now this here is deterministic. Right? W is known, the amount I need to pay for the coverage P is also known, so W minus P is known, and the utility function of W minus P is also given. Right? So that's constant, we don't need to take any expectations. So when do you prefer insurance over no insurance? If you have this inequality. If taking insurance increases your utility. So you look at what is my expected utility when I do not take insurance. What is my utility when I take insurance? If that last one exceeds the first one, it's better to take insurance. I'm better off in terms of expected utilities by taking insurance. All right. Everyone understands, agrees on this inequality, right? And if you have a decision maker that has to make two different decisions, say taking insurance with full coverage or taking insurance with a deductible, you do the same. You look what's the expected utility in the first situation, what's the expected utility in the second situation, and the preferred choice is the one that gives you the highest expected utility. Right, so now I can make variations on insurance contracts with a deductible, quota share insurance where you pay like X% of your loss. You can think of different situations. I think there are some examples in the exercises, but the idea is always the same, right? You look at what do I get for utility in one case, in the other case, and you compare. Okay, so that's what I have here. I prefer insurance when this inequality holds. Assume now that your premium P is equal to 0. So assume that I can take insurance without cost. If you then look at, at this thing here, expectation U W minus X. X is positive, right? It's a loss. So what you have here, this here, is always smaller than U of W. right? Because X is positive. So you find that this here is always smaller than U of W, which is equal to U W minus P if P is 0. So it means that if your premium is 0, you always take the insurance. Why? Because you can get rid of the loss with no cost. That's a sure gain that you get basically. So for P is 0, you always take the insurance. If you take P very large, so if you look at this left hand side, you have U is a non-decreasing function. P, you have minus P, meaning that here if you increase P, W minus P becomes smaller and smaller. Your utility of W minus P becomes smaller and smaller and smaller, right? So this thing, P to U W minus P is decreasing in P. The larger you take P, the smaller that quantity gets. Okay, that's on the left-hand side. If you look on the right-hand side, this expect utility does not depend on P. Right? You can just calculate, if I suffer this loss, this is my expect utility. Right? So you have a fixed level for your expect utility, and your utility, in case you take insurance, goes down in function of the premium. Okay, so what we get is that if P, I put a premium here, P is 0, so here you have the utility U of W. And somewhere, let me take a different color, green, you have the expect utility, expectation U W minus X. I know that if P is 0, U of W will be above this green line, because that's what we just showed, is that in case P is 0, you always take insurance. Right? So U of W is always larger than expect utility, that we know. And your line here, which when I plot this line here, which is the blue line, is U W minus P, this blue line will decrease. It will decrease, and if we assume that U is a concave function, it's also a continuous function. So the blue line in function of P will decrease in a continuous way, meaning that at some point it will cross the green line. It cannot jump over the green line because it's continuous. It has to cross, and this crossing point here is what we call P big M, which we know exists. Okay? If you then have a look at this PM, you see that in between 0 and P big M, your blue line is always above your green line, meaning that for premium 0 until PM, you prefer to take insurance. Taking insurance will increase your utility. For any premium P that exceeds this PM, you prefer to take the risk. It's better to take the risk X yourself instead of insuring it. Why? Because the premium is too expensive. You are happy with the insurance because you get rid of the risk, but the price you pay is too much. So this P big M is what we call the maximal premium. It's the maximal amount you're willing to pay for insuring the risk X. If someone offers you a contract for a price PM or less, you're fine. It always improves your utility. Otherwise, you're not taking the insurance contract. All right? Everyone follows the ideas here? Yes? Okay. If you use Jensen inequality, so let's for the moment start with this expected utility. So this is the expected utility when you suffer the loss X. so I'm not insuring it. If I apply Jensen's inequality, I assume that U is a concave function, meaning that my decision maker wants to get rid of the loss X. I have this inequality, and I can swap the expectation and the function U. So instead of taking the expectation of U of something, I take U of the expectation of something, the expectation W minus X, which I can write as U W minus the expectation of X. All right, so what we see is that this is the situation where you take no insurance. This here is a situation where you are taking insurance for premium expectation of X. That's this insurance with premium expectation of X. So you are swapping your risk X and you're paying the expectation, your expected loss. And then the inequality tells you that if you can swap your risk X for the expectation, it's always better to do so. So insurance for a premium that's equal to the expectation, it's always better than taking no insurance. So the expectation of X is somewhere, say, here. It can be equal to PM, but it can never be larger than PM. Because expectation of X means a premium equal to expectation of X means I take insurance. So it should lie in the interval 0 PM. And that's what we have. What we have here. So two important conclusions here. If I'm a risk-averse decision maker, then I can find a maximal premium, PM, such that everything below that premium is a good premium, meaning that I'm willing to insure for that price. First conclusion. Second conclusion is that maximal premium is always larger than the expectation of X. I'm always willing to pay more than my expected loss. And the difference, so if you look at P and the maximal premium you are willing to pay minus the expectation of X, this you can think of as a kind of a loading that you are willing to pay on top of your expected loss because you are getting rid of the variability. You swap uncertainty for certainty. You're getting rid of your random loss. In return, you pay a fixed price P, and you're willing to pay more than expectation because, well, you prefer the certainty over the uncertainty because you are risk averse. Okay. Everyone understands this? Clear for everyone? So if you have questions, feel free to ask or put them in the chat. But if not, very well, then we can continue with the other side. So now we are moving to the insurer. We are an insurer now. We are having a utility function U, an initial wealth big W, and we have to decide, should we take on a certain risk X or should we not take it? Is it acceptable for us or is it not acceptable? And we can do the same as we did for the individual. So now we have the insurer here. The insurer can do two things. It can, let me see. I want to know if we can have a case where PM is less than the expectation. Okay. So you have for a risk averse decision maker, meaning a decision maker with a concave utility function. That's what we proved on the previous slide. We always have that the maximal premium PM is larger than the expectation of X. Always. If you turn it around, if you take a convex utility function, meaning a risk-loving decision maker, then you will find that PM will be smaller than the expectation of X. Right? Then you are not willing to pay more than your expected loss because you like the gamble. Okay, but in this case, we always assume that you are in this situation. Now we are doing insurance, meaning that by nature we are prudent. We don't want to make a risk management framework, Solvency II, that allows for risk-taking individuals. That would be a little bit the world upside down. So here we are in this situation. Of course, if you think on gambling, a casino, probably you are in the convex case. Almost by definition, if you step into a casino, you want to take on risk. You want to swap your money for something that is random, a random income. Okay, does that answer your question? Okay, no, I was here. Okay, we are with the insurer, and the insurer can decide to not accept the risk. So if you do not accept the risk, you have an initial amount W, then nothing happens. You stay with your amount W. So this is the corresponding utility. Everything remains as before. In case you accept the risk, you have an initial amount W. Because you accept the risk, the policy or the insured individual will pay you a premium, so you can add that premium to your capital. So your capital will increase because you receive the premium, but now you have to pay the loss X, you have to subtract X. So your capital goes up because of the premium, it goes down because of the risk. So this W plus P minus X will be your fortune after you receive the premium, you suffer the loss X. The corresponding utility is then this, and we take expectations because now we have a random utility. So this is the utility after suffering the loss X. Okay, and the insurer will accept the risk X in return for P if we have this inequality. All right, so you receive P, you pay X. Okay, and oops. And if you have a look, then U is an increasing function, and now you have plus P. You have plus P, meaning that right-hand side will be an increasing function of P, which makes sense, I hope to you, because the more premium the insurer receives, the better for him, right? So that left-hand side will remain the same. If the insurer is doing nothing well, its utility will always be U of W, and that right-hand side will be an increasing function of P, so we can again look for the point, which we now call P small m, where the two are exactly equal. Again, using concavity of your utility function U, you have continuity, and you know that this thing here has a solution. Right? You cannot jump, you cannot have a P where you are below U of W and then suddenly you jump over that level. That cannot happen because you have a continuous function. All right, this PM here is now a minimal premium, right? Because now you are in a situation where you have here U of W, the utility when you are not insuring anything. You have the premium P here, and your expectation U W plus P minus X. The blue line is an increasing function of your premium. So this point here, where the two cross, P small m, is a minimal premium, meaning that if we are above this PM, the blue line is above the green line, meaning that you prefer to take the insurance. Right? So the insurer says, I want to receive at the minimum amount of PM. Of course, more is always preferred, but I need to receive at least the amount PM. That's my minimal amount I want to receive in return for insuring X. Right? So for the insured, it was a maximal premium. For the insurer, it's a minimal premium. Right? The insured wants to pay the maximal premium or less. The insurer wants to receive the minimal premium or more. All right? And then we find that we have a feasible contract, meaning that both insured and insured can improve their expected utility if we can find a premium P that is in between the minimal premium of the insurer and the maximal premium of the insured. If the minimal premium of the insurer is larger, exceeds the maximum premium of the insured, you cannot come to an agreement. If you set a premium, there's always one party that is not improving its utility, so it's not willing to enter in the contract. Right? So in order to get a feasible contract, the minimal premium of the insurer should be smaller than the maximum premium of the insurer, because then there is space in between where you can find a feasible premium. Right? And every amount in this interval, so whatever P you take, as long as it exceeds the minimal premium, it does not exceed the maximum premium, both parties are willing to insure for that price. Yeah, because it's optimal compared to the other choice. Okay? Clear for everyone? Yes, very good. A good exercise to try is to try this equality. It's slightly more difficult than the same inequality for the insured, for the individual. But it's a good exercise. Again, you basically use Jensen's inequality. But have a look to show that also the insurer requires that you pay more than your expected loss. So the insured individual is willing to pay more than expected loss, because you are very happy that you get rid of your loss, so you want to pay a bit more. The insurer is requiring a loading to take on the extra risk, because also the insurer is risk averse, so he wants to get some compensation for the variability that he takes on, and that compensation is exactly this difference. The difference between the premium he requires and the expected loss. All right. Everyone is still following here? Yes. All right, very good. Let's take a break of say 10 minutes, and then we continue with the mutual exclusive part. So if you have questions in the meantime, put them in the chat, and otherwise I will see you back in 10 minutes. And before I continue with the last part of the slides, I want to do an exercise. So I think it's exercise 2 of the exercises. It's 2. I want to focus on the main idea of this exercise. You can do the exact calculations yourself. I hope that by the end of this chapter, calculating expect utilities and like playing around with these formulas is relatively easy. That should go fast. We want to focus a bit on the interpretations. All right. So assume that you have an insurer with initial wealth W, which is equal to 100,000. 100,000 wealth initially, and you are facing a loss X, which is equal to the probability that X is equal to K. It's 1 over 3, where now you have 3 possible losses, or you have a loss of 0, no loss at all. You can have a loss of 1,000 and a loss of 100,000. So it means no loss, a small loss, or a very big loss. That's a bit the idea. And assume that everything happens with the same probability 1 over 3. And you can think of X as the total risk situation of your insurance company. So you are an insurance company, you have sold many policies, you invested your money in stocks and bonds and maybe other assets, and then you put that all together, you have losses, you have gains, you put it all together and you say, well, these are on the aggregate level my possible losses, right? So here I take a very simple example, but again, you can extend this example and assume that X is a much more realistic, complicated distribution. But let's not make life very complicated by taking very, very complicated distributions. Let's focus on a very simple example. Okay, and the question is, what is the value of your liabilities? So X are liabilities, things that you have to pay, right? You cannot make a gain here. You only focus on the liability side. What's the value of these liabilities? Okay, and maybe you took a course in loss models or a course in life insurance. It's also on valuing future liabilities. Here we take an approach using utilities. So we say the value of the liabilities is the following. We denote it by V, and V is determined using the following equation. You look at the expected utility when you are just facing the losses X compared to the utility when you are transferring your loss to another party, right? So I value my liabilities by using an insurance, or in this case, reinsurance premium. For what price, what's the maximum price I'm willing to pay to get rid of these liabilities? That's how I value my liabilities. Okay, everyone agrees, understands a bit the idea of this definition. Okay, and here I assume that U, my utility, is the square root function, which is a concave function. Okay, this is the situation. And the first question is then, what is V? Right, what is V? And how can we calculate V? So determine V, that's the question. How can we determine V? We first calculate this expected utility. U is equal to the square root function, so the inverse is the function x to the power 2, right? So then we calculate the expected utility to the power 2, and then we solve for V. That's what we do. Okay, so we calculate first the expected utility, W minus X, which is equal to, probabilities are always 1 over 3, so it's 1 over 3 times your X, your random variable can take value 0, 1,000, 100,000, and W is equal to 100,000. So you get, in case X is equal to 0, you get 100,000 minus 0, square root times the probability 1 over 3, right? Plus probability 1 over 3, the situation where you have 100,000, but now you suffer a loss 1,000. Plus 1 over 3, you have 100,000. and you suffer a loss of 100,000. This is your expected utility, right? Everyone agrees with these calculations? Yes, I hope so. You put that in your calculator and you find, what do you find? 210.2901. This is what you find. Okay. Then you take this equation here and then you find that V is equal to W minus U minus 1, the expected utility. Right? You put the U function to the other side, you solve for V, you get this. Right? Which is, in our case, 100,000. U minus 1 is the function x squared, so you get 210.2901 to the power 2. Yes? And then you find 55,000, something like this. This is your value. Okay? Everyone understands these calculations? If not, please let me know. Because again, the focus is not on the calculations, right? I want to show you something with this example. Okay, so we find the value is 55,787. Okay. Assume now that this insurance company is trying to manage the risk better. Maybe you are saying, well, losses that can top 100,000, so a possible loss of 100,000 is too dangerous for us. Meaning that if we are in that scenario, we are losing all our money. It's too dangerous. We are going to sell some losses or buying reinsurance or whatever. You are doing your risk management a little bit better and you reduce your maximum loss of 100,000 by 20,000. Right? So the insurance company is doing something and now the new liability, it's not X, it's Y. And now again, you have 3 possible outcomes for Y. The outcomes 0, 1,000. So that's are your normal situations. That's fine. It's just instead of having this maximum loss of 100,000, I now can only get at most 80,000. Right? So you do something, meaning that you avoid extreme risks. You buy insurance, reinsurance, whatever. You hedge parts of your risk. You do something, but you get rid of the extreme amounts between 80 and 100,000. That's what you do. All right. And then the same thing, determine the value of your liabilities, which I now call VY. Yeah, it's the value of your liabilities, but now it's Y and not X. You use the same calculation as before, right? The only thing that changes is this part here, right? You go to the same calculations and you find, you find that VY is equal to 33,729.49. Okay. And if you want, you can calculate VY divided by V to get an idea of the reduction that you have. You get something that is around 60%. That's correct? No. So it means by reducing your most extreme risk, in this case by 20,000, the value is reduced by 40%. Okay? Assume that, well, if you see, well, this is actually a good thing, right? You are the boss of your company. You say, well, by by reducing my most extreme, it's not that I'm rearranging my whole portfolio, right? I'm just looking at these very extreme risks. For example, you say, instead of investing in these very, very risky cat bonds, that with a very low probability I have to pay a lot, we're not going to do that anymore. You reduce your risk slightly, you get a reduction in your value of liability by 40%. Right? That's a good reduction. You say, well, we want to do more of this. And we want to reduce even more, and we go to call it the value z, the random variable z. Again, we have 3 outcomes, but now 0, 1,000, and the maximum amount is 60,000. Right, so 8,000, 60,000. We say, well, we want to again have that reduction of 40%, so let's reduce a bit more. Right? You go to the same calculations, you find that VZ, the value of your liabilities, is now equal to, let me see, it's 23,729. No, yeah, no. 23,294. This is your value of your liabilities. And the reduction, when I reduce my my maximal, my extreme risk by 40,000, from 100,000 to 60,000, so I reduce it by 40,000, that reduction is now around 40, say 42%. Okay. So what do you see? Important observation. If I reduce my most extreme risk by 40,000, so for the X random variable, it was 100,000. For the Z random variable, it's only 60,000. Then my reduction in the value of my liabilities, it's around, say, 60%. But that 60% is not equally divided over the first 20,000 and the second 20,000. The first 20,000 accounts for 40%. The last 20,000 accounts only for the remaining 20%. Right? So what does it tell you? It tells you that assume that you are looking at your liability, your extreme risk, and you say, well, I cannot reach that reduction from 100,000 to 60,000. It's too difficult. We have to rearrange too much, which also comes with a cost. That's too much. Then it still pays to go for the 20,000 because that has a much larger impact than that last part. So just changing small part of your risks, which maybe on the level of the risk itself do not look like very impressive, right? Going from 100 to 80,000, you say, well, we reduce the extreme risk a little bit, but well, what does it matter? You see that because we use concave functions, it matters a lot. Yeah, so even if you do not have, say, the perfect solution, even if you say, well, we really want to go to that 60,000, and if that's not possible, we don't do it at all, that's probably not the best solution. The best is to go for what might be for you not the best, not what you desire. Go for the first 20,000 because that has the most effect. Right? I put the two papers, one is in Dutch, one is in English, on wearing face masks on Toledo. I also shared them on the Facebook page. It's a bit on this idea. When you were following, and still now, the debate on face masks, but it's in general on what should we do to tackle, to prevent spreading of the virus, you can look at the individual studies where you say, well, how effective is a face mask, right? And you see, well, it's maybe not the perfect solution. It doesn't protect 100%. It probably doesn't even protect 50%. But the spread of your virus is a convex function of the effect of your face mask. Meaning that if you can, with a face mask, can get a small reduction in the spread because of convexity, non-linear effects, it can have a huge impact on your number of infections. Right? Same here. You reduce your extreme risk a little bit, but that first reduction has the biggest effect on your liabilities. Right? And that's why sometimes, because of non-linear effects, concave, convex effect, depending on what situation you are, it doesn't matter that you do not find the optimal solution as long as you know what is the direction of your improvement. And if you draw the function, so the function where we have, I call the maximum amount 80,000, 60,000, let's call that M. Yeah, I put M here. Then that's on the y-axis I put V. Then you have a convex function. U is concave, but V, let me see. This is V, right? Because you have U minus 1, you get something convex. You see that if here is your maximum loss, if you can only reduce it by a little bit, because of convexity, if you have already a very high M, your reduction, it's quite impressive. The smaller your maximum loss gets, the lower your reduction is. The less important it is to really focus on reducing your maximal extreme losses, right? Which is all caused by non-linear, in our case concave and convex effects. When you have uncertainty and you have a concave or a convex effect, sometimes you can make decisions by just knowing what is the direction of your improvement. If it is convex, if you go a little bit to the left, we can get huge reductions. That's what you see here. And then you also see that if you want to get the same improvement, the same reduction of 40%, in question C, you need to reduce your maximum loss by more than 20,000. You need to reduce it more, you have to do more efforts to get the same effect. All right. I hope it's a bit clear. It's important. It's important to understand risk, and you will see that throughout the rest of the course we are talking about risk, concave, convex functions, risk measures, relations. They are automatically tied to that. If you want to understand risk, we have to understand non-linear, concave, convex effects. These are basically the same thing. Okay, clear for everyone? Yes. Okay, I hope so. Let's now move to the last part of this chapter, where I want to talk about what happens if you are facing multiple risks. So until now, the problem was always, I have a decision maker who is facing or risk X or risk Y. Right? And then we can calculate expected utilities of X, expected utilities of Y. But now assume that, and for simplicity, let's just look at X1, X2 together. So I put them in a vector notation, meaning X1 is a risk, X2 is a risk, and I can look at the distribution of X1. So what's the probability that X1 will be really large, small, zero, whatever? The distribution CDF of X1, which I denote by Fx1. I can do the same for X2. So assume that you have data. X1 is a car insurance loss, so you have car insurance data. You put it in R, in MATLAB, in Python, whatever you use, and you do some statistics to get a distribution of X1. And then you have X2, which is on housing and losses, damage to houses. You put that data also in Excel or in R. You do the same analysis. You also get a distribution for X2. So it means that you first look at X1. What is the distribution of X1? Then you look at X2. So in this CDF, for example, there is no information of X2, right? Because in your think about your statistical analysis, you only looked at the column with values with losses of your car insurance portfolio, right? You just could delete the other column and then you do the same for X2. But if you think of X2, X1, X2 as, for example, car damage, house damage, if I'm insuring both losses, I have a policyholder that has a policy for his car and a policy for his house. I'm interested in what is the probability that I have like a real large loss on your car. What's the probability that you have a real large loss on your house completely burns. But I'm also interested, what's the probability that both extreme events happen at the same time, right? Because that would be really bad. Then I'm losing money on one policy and the other policy. And that probability, right, that you have two events at the same time, you cannot determine it from fx1 or fx2. Because the CDF of x1 does not contain any information on x2 and vice versa. Meaning that if I know x1, meaning I know the CDF of x1, I know the CDF of x2, I also have to model how do x1 and x2 move together, right? And you know already one situation, it's independence. Yeah, where the probability that x1 is large and x2 is large is just the product of the two. Yeah, that's the most easiest. X1 smaller than small x1, x2 smaller than x2 is just the product of the two. But this is just an assumption. Here we assume that they are independent, that they do not interact with each other. Another situation could be where they are what we call mutually exclusive. What does it mean? It means that if you look at the probability that I have a positive loss on one random variable and a positive loss on the other random variable, that event occurs with probability 1. Meaning, think about your car insurance, your house policy, that if you have a loss on your car policy, you will never have a loss on your house. That's mutual exclusivity, which is different from independence. We model how things move together in a different way, right? Think about, for example, a life insurance policy where you say for a term of, say, 20 years, I pay you 500,000 when you die within that 20 years. And if you survive, you get some survival benefits, right? These two risks, the risk that you have to pay the death benefit, the risk that you have to pay the survival benefit, are mutually exclusive risks. Because if I know that I pay the death benefit, I know for sure I will not pay the survival benefit, because once that, you cannot survive anymore. In the other situation, when you do not pay the death benefit, you will pay the survival benefit. Right? So these are mutual exclusive risks. There are two payments. If I only look at the survival benefit, I'm afraid I have to pay the survival benefit. If I look at the death benefit, as an insurer, I'm afraid I have to pay the death benefit. It's not good for me, right? I have to pay a lot of money. But at least you know that the two events do not happen at the same time. Right? So you are in the good case in one situation, the bad case in the other situation. Okay? Everyone is still following me? Yes, very good. So assume that I have multiple risks, x1, x2, x3. Assume that these are losses of different portfolios. For example, I have a portfolio in US, in North America, I have one in Europe, I have a portfolio, an insurance portfolio in Asia. 3 portfolios, but I'm one big company. Then If it happens that I have lots of losses in Europe, so my portfolio, my business is making losses in Europe, of course, what you hope is that you look at China, at Asia, you look at North America, and you see some gains there, that you can offset these losses. You want that your portfolio is diversified. Then, in case you have independence, then what happens in, say, North America and Asia is independent of what happens in Europe. If you have that they are very positively dependent, assume that you are in health insurer, then you are facing losses due to COVID-19 all over the world. It means that you look at Europe, you see losses because of COVID-19, and you know already, well, this happens also in North America and Asia. There's not too much hope that I will make profits there. Yeah? The losses, the trigger for the losses in Europe is the same as in North America and Asia. Your losses are positively dependent. If your losses are high in one place, it's more likely that they will be high in the other situations. Yeah? That's the suboptimal situation. That's the situation you want to avoid. Yeah? You don't like that. You want the other way around. You want that if you have losses in one place, that it becomes more likely that you have gains in other places. That's a good situation. So the bad situation if things move together. The good situation is if things move in the opposite way. Right? Everyone agrees on that? Yes. Think about your investment portfolio. Maybe yesterday you made a huge profit on Apple, but also losses on some other products. Right? You want that they move in opposite directions just to cover your losses. Mutual exclusivity, what we have here, is a very extreme situation of what we call negative dependence, these losses that move in the opposite way. Because it tells you if I have losses in one portfolio, for sure, I will not have losses in the other portfolios. Right? So it's the most extreme case. So if I see that my portfolio in Europe is making losses, I say, well, luckily the other two portfolios will, the probability one, not make any losses, which is a very extreme case. In reality, you will not have that the probability is 0 to have losses. It's just a low probability, right? That would be the more realistic case. So mutual exclusivity is an extreme situation where your losses are moving in the opposite way, right? So in that case, or in that sense, your mutual exclusivity, it's what we call the best case scenario. The worst case scenario is if with probability 1, everything will be very positive at the same time. And later in this course, we will talk about comonotonicity, which is exactly modeling this worst case scenario. And why do we focus a lot on comonotonicity, a whole chapter on comonotonicity and only one slide, no, 2 slides maybe, on mutual exclusivity? Because modeling negative dependence turns out to be very complicated, whereas, as we will see in the chapter on comonotonicity, modeling positive dependence, things that move together, it's a bit easier. Not a bit easier, it's much easier. Why is that? Think about 2 losses, right? Again, your x1, x2. I can say, well, x1 and x2 are very positive dependent. They move very strongly together. Think about your stocks, right? x1 is your first stock, x2 is your second stock. If they are moving together, means that if I see that my first stock is having big profits, it's very likely that my other stock will also be very large. If my first stock is getting lots of losses, it's minus 10%, very likely that my second stock will also be very small, right? If I now add a third stock to that, which is also very strongly dependent with the other 2 stocks, it just means they all go up together or they all go down together, right? And if I have 2 stocks, 3, 4 stocks, 4 stocks, 5 stocks, 50 stocks, is all the same, right? Everything goes up together, meaning you have green on your returns for all your stocks, or you have, they go all down together, they're all red, right? Positive dependence, you have 2 stocks, 3 stocks, 5 stocks, very easy to understand. Now do the same for negative dependence. You have 2 stocks, negative dependence means if stock 1 goes up, stock down, stock 2 will go down, right? Or if stock 1 goes down, the other one has to go up. So it means that stock 1 goes up, the second stock goes down, negative dependence. But now assume you want to add a third stock. What should the third stock do? Should it go up or should it go down? If it goes up, it's negative dependent with your second stock, but positive dependent with your first stock. And if it goes down, it's the other way around. So negative dependence is much more complicated to model. And it turns out there's not like a unique best way. Everyone agrees that commonotonicity is the way to model positive dependence. But how to model negative dependence, that's not so clear. Mutual exclusivity, it's one possibility. But you can also say, well, if I have multiple stocks, X1, X2, X3, say, I say that they are negative dependent if the variance of the sum is equal to 0. It means that x1 plus x2 plus x3, if I add everything, it should be a constant, always the same value. Meaning that if x1 and x2 are very large, x3 has to be small to go back to that same level. If x1 and x2 are very small, x3 has to be large to compensate. Again, you have this compensating effect that you also have with mutual exclusivity, but it's a different way. It's a different way to model extreme negative dependence, right? So mutual exclusivity, it's extreme negative dependence. This is a different way to model negative dependence. It's what we call mixability. Okay, but we stick for the moment to mutual exclusivity. So assume that you have a decision maker with utility function u, and just to keep the formula simple, I assume that uw is equal to 0. In the course text, which I will upload, I think, next week, you will have a proof where u of w is different from 0, but that's basically the same proof. So if I now assume that x and y are mutually exclusive, so they are losses, so they are positive, but they cannot take strictly positive values at the same time, mutually exclusive. And now we have a decision maker with initial wealth w, who is suffering both losses at the same time. So this would be the expected utility when you have x your car loss and y your home. Right? You are suffering x and y at the same time. Then this is your expected utility when you suffer both losses at the same time, and we can prove that you can write this expected utility as expected x plus the expected utility when you suffer x plus the expected utility when you suffer y. What's important here, first thing that is important here, is that if you look at the left-hand side, you have an expectation, and inside the expectation you have x and y. So if you calculate that expectation, yeah, you take the integral, you need to join distribution of x and y. You need the probabilities of x and y taking some values simultaneously. On the right-hand side, you have two expectations, but each of these expectations only contains one risk. So I can calculate the first, this one, expected utility, using the CDF of x. And the other, this one, I can calculate using the CDF of y. All right, so if I have the CDF of x and I have the CDF of y, I can calculate the right-hand side, but I cannot calculate the left-hand side directly. Yeah, with this theorem, you can link the two. You can start from an expected utility of X and Y where you think, well, probably you need to join CDF here, but then you do some calculation and you see that it decomposes in X, in a part with X, a part with Y. Okay, it's what we call a decomposition formula. And important here is that we need that they are mutual exclusive. Okay, that's the first important observation of this formula. So I'm not going to give the proof here in the lecture. So you find in the videos, which I will upload later this week, you find a detailed proof, and I think it's much easier to follow that proof than when I do it here on my slide. But have a look at the proof. I think it's not too complicated, but it's a good exercise if you can still work with conditional probabilities, right? And we will use that, the ID that we have in the proof with the conditional probabilities and the mutual exclusivity. We'll use that also in the exercises, I think next week or the week thereafter. Okay, so for sure have a look at the proof. Okay. So in case you, well, no, let me do that later. Let me look at a second important observation of this result. So first of all, note that X and Y are losses, and we assume that they are positive losses. Yeah, car insurance losses, your damage to your house, that type of losses. That's what we're looking at. So then the expectation of U W minus X and the expectation U W minus Y, these are negative, right? Because you subtract always things, so they're negative. Assume now that you suffer the loss X. Yeah? So it means that, assume that, well, let's say you suffer the loss X. Then we can say, well, today we have a wealth of W and your utility, it's at this level. And we assume that that level is 0, right? That's before you have any loss X or Y or X and Y. Now it turns out, so for example, you are exposed to the risk X. It means that you will suffer this loss X, so your utility will drop. Yeah, and it will drop to, say, this level here. Right? And this difference here, yeah, which I can call, for example, delta. Delta is the drop in utility from being exposed, from suffering the loss X. Yeah? So delta is UW minus the expectation UW minus X. Where in this case, we assume that UW is 0, but in general, you get this delta. Okay? So now assume that X and Y are equal in distribution. That means that this delta is also the drop in utility when you're being exposed to Y. Right? It's the same. Okay? In case X and Y are equal in distribution, then your formula becomes, so the formula that we proved, this one here. So in case X and Y have the same distribution, the two expectations on the right hand side are the same. So we get the expectation U W minus X minus Y, yeah, is equal to 2 times the expected utility U W minus X So assume now that I'm thinking of adding loss X, loss Y to my portfolio. Right? So I go first from no risk to the loss x, then my drop is delta. Assume that I'm now at this level here. I say, well, let's now move here to, make this small, this to expectation u w minus x plus expectation u w minus y. So I say I'm going from no loss to a loss x, first drop in utility, and then I say, well, assume that, well, I suffer the loss x, I'm reaching that expected utility of x, and then I add, after I suffer the loss x, I add the loss y. Yeah, and then I have another drop, which, if they are equal in probability in distribution, is again delta. Does everyone understand what I'm doing here? I'm adding x and y, but I'm adding them one by one. First, I face the loss x, then I stop. I reach, well, I don't know what x is, so I assume that, well, I reach my expected utility, expectation u w minus x. Then I'm adding the loss y. Yeah? And if I assume that my decrease in utility in these two times is delta, my drop in utility will be 2 times delta. Right? I can also say, so that's on this figure here on the left. I can also say, let's take this level here, and now I'm adding x and y at the same time. So I'm adding it at the same time. So I'm being exposed to x and y at the same time. So my utility is now expectation u w minus x minus y. I'm adding them at the same time to my wealth. So then I end up somewhere, say here. Where that red line is below, what color should we take? Yellow, to this yellow line. That's what we, no, it's equal, sorry. Here it's expectation u w minus x minus 1, right? So if I add both risks x and y at the same time, my utility drops from u of w all the way to that expectation, which, that's what we proved here, is exactly a decrease of 2 delta. Right? So I'm adding 2 risks separately, or I'm adding them simultaneously. It results in the same drop of utility, so you end up with the same happiness after you're facing these 2 risks. Right, so you have, do it here. This is, you add them separately, and this is jointly. It's the same. Or you can say, when I'm facing 10 risks, it's just 10 times the effect of 1 risk. It's linearity. Yeah, it's linearity of your utility, of your happiness. Can everyone follow this idea, this interpretation of your expect utilities and how you add your risk to your portfolio, jointly or separately? Everyone understands? Clear? You're sure? Okay. Because it's very important. It's important because what does it mean? It means that you are looking at a risk, right? You're looking at a risk and you say, well, based on this single risk X, I know it's a risk, so I know that my utility will drop. I know my utility will drop, but I'm looking at the delta, the drop in utility, and I say, well, this is acceptable to me. Right? It's acceptable to me. Then you think, how many risks can I add? Then normally, what you like, the human brain is in most cases is a linear brain. You think if I'm exposed to 10 times this risk, probably I can bear it, because you think, well, 10 times that small risk, still acceptable, so that works for me, right? And that's what you see here. But here we used mutual exclusivity. We used that if I add lots of risks, then they cannot be big at the same time. Mutual exclusivity. We are in the optimal, the best case scenario. So let's have a look at what happens when we do have functions, when we have risks that are not mutually exclusive, right? Okay, we first need a lemma. Assume you have a concave and non-decreasing function. Function u, we call it. Then for a number a in R, so I assume that u is real valued, otherwise you have to restrict the domain of a, but assume it's real valued, and define on R, and I take alpha 1, alpha 2, these will be my increments, I take them positive. Then we have that u a minus alpha 1 minus alpha 2, then this is smaller than u a minus alpha 1 plus u a minus alpha 2 minus u of a. So I leave the proof for you. You can try the proof. It's not a complicated proof, but you really need to use that property of concave functions, where you see that if I subtract or add something, then the effects on u becomes smaller when you move up, or becomes bigger when you move down over your function. We saw that that property when we introduced concave functions, and we looked at the attitude of concave utility functions when receiving money, right? That argument you want to use here, all right? But if I use that lemma, so use this lemma to prove the following. Again, I'm looking at this expect utility, w minus x minus y, but now x and y are not mutually exclusive. Can be two risks, x and y, they can be independent, can be very positive dependent, can any combination of two risks. Could be mutually exclusive, but not necessarily. Then this, again, this expect utility is the utility that you reach if you suffer x and y at the same time, simultaneously, right? Then we have an inequality now, not an equality, but an inequality, and we have, again, the two, what we call marginal expect utilities, meaning an expect utility only having x, only having y. Okay, minus u w. Okay, so I leave the proof of this to you. If there are problems, if you have questions, please ask me. I think it's good to try it yourself. It's not a long proof. I think for me to write down the lemma, even plots, to visualize is like 2 pages. Okay. But we want to focus on the interpretation. What do we, what can we get out of this? Okay. Assume that you are adding the risks X and Y simultaneously to your portfolio. Then, as I explained before, UW minus this expected utility. Yeah, so you're not facing any risks, so your utility is UW. Then you're adding X and Y to your portfolio, then your utility drops to that expected utility. So the difference is your decrease, your decrease in utility when adding X, Y jointly or simultaneously, right? And if I look at UW minus the expectation UW minus X, this is the decrease when adding only X, right? Same as before. Okay, so what this inequality tells you now is that UW minus the expectation UW minus X minus Y. So your loss in utility when you're adding X and Y simultaneously, this is bigger. Yeah, you have here this inequality, you have the minus in front of the utility, so it reverses. It's 2 times UW minus expectation UW minus X, provided X and Y are equal in distribution again. Yeah, where this is what we previously called delta. All right. So what you see now is that if I'm adding X, or if I'm investigating what happens with my utility when I add X to my portfolio, and I see my effect is a loss of delta in utility, my happiness will decrease by delta. Then I say, well, if it is only delta that I lose, I can bear, I'm okay with losing 2 delta, so let's add X and Y to my portfolio. If I do that simultaneously, my loss in utility is larger than when I do it separately. So here we have that this is adding X and Y jointly or simultaneously, and this is doing it separately. And if you do something separately, the effect is smaller than when you do it simultaneously. Why is that? Because we have to assume here that U is a concave function. Again, this non-linear effect, because we use non-linear function, concave functions in this case, your extreme events, where you lose a lot of money, are punished more severely than your positive effects. Right? Meaning that adding things simultaneously and running the risk that you have losses simultaneously, which are very large, is having a bigger drop in utility than when you do it in a separate way. Which again is important to keep in mind, because in most cases when you do decision making, you are thinking on the case where you add them separately. If you are, for example, thinking on the investment, then in most cases when they show you a plot of how your investment goes, it's constructed in a way where you simulate all your returns in a separate way. First for the first year, then the second year, then the third year, which is different, has a different effect when you're exposed to that whole path simultaneously, where you run the risk that all your returns are small at the same time. You're very afraid of that. If you do it in a separate way, if you approach the problem in this separate linear way, it gives you the wrong results. You are too optimistic on the outcome compared to when you do it simultaneously. So it leads A, to the wrong conclusion, and B, the direction of your outcome is also in the wrong way. Right? You will be less happy when it turns out to be simultaneously and you were approaching the problem in a joint way, in a separate way. Right? If the inequality would be the opposite, it wouldn't be that dramatic. If you then approach things in a linear way, in reality they are concave, but you say, well, it doesn't matter because the linear way is always a lower bound in happiness for the concave way. So in reality, I will be more happy than my predictions. That's fine, right? That's no problem. But here the inequality is in the wrong side. You will lose more utility than your model predicts, your linear model predicts, right? Which is a little bit the same as what we did in the exercise, right? We add a decrease of 20,000 and another decrease of 20,000, but the effect it has, if you put them together, it's not the sum of the two standalone effects. It's a little bit the same, not a little bit, it's related to what we do here. Doing things separately, doing things jointly with concave utility functions is different. You will be, in most cases, you will be less happy in the joint case, the real case, than when you do it in a linear way, right? Which is, again, a very important aspect of concave, convex utility functions. Maybe to conclude, one example that maybe can help to understand a bit what is going on. So assume that we look at this expect utility and assume that I add multiple risks, right? And assume that x1, x2, x3, is the risk that you will fall from something. You are standing on a ladder, and if x1 can be 0, meaning you do not fall off, x1 is say 1 meter, you fall off your ladder. W is your current situation, and assume that w minus x1 is your utility that you reach when you fall off your ladder, meaning that you will get some pain, right? You fall, if x1 is 0, well, it's fine. You do not lose utility, you do not get any pain. If x1 is 1 meter, well, you fall off a ladder of 1 meter, you will have some pain, right? Then you can say, well, I can look at my utility, my pain that I expect to get of falling off 1 meter, and I can do that. I have to move this thing here. So I can do that, say, 10 times. Or make it more dramatic, 100 times. Right? You are working in your house, washing and repairing stuff, and 100 times you climb on a ladder, 100 times you have the risk of falling off, right? And you can look at 100 times the pain you get of falling off that ladder, right? If you fall off 100 times, 1 meter, that's not too nice. You will have some pain. You will not sleep very well that night. Maybe also the next night, but you will recover from that, right? If you then look at this thing here, this is the pain that you get when you are not falling off your ladder, your 1 meter, one at a time, but you do it simultaneously. The meters add up. In the worst situation, x1, x2, x3 are 1 meter, so you fall off 100 meter. If that's the case, you will be far worse off than 100 times that marginal pain. Right? It's not that you will, if you fall off 100 meters, that you will not sleep well in the next week. Probably you will sleep forever. Right? So the pain here, when you do that simultaneously, is much, much more than the pain of doing that step by step, right? Meaning that your scale is important. 100 times 1 meter is different than 1 times 100 meter. You try and you will see, right? The same happens with investments. If you are having losses, if you have, say, 100 banks or say 1,000 banks with a loss of 1,000, and they have to settle that claim, right? You are buying options and swaps and everything, and you have losses, so it means that you want to get rid of the losses, so that costs you money. If you have lots of banks that have small losses, it's most cases is okay. No one will even really notice what's going on, and you can easily settle your losses, right? It will be some pain. Yeah, your manager, your CEO will not be happy. Maybe you get fired, too bad for you, but the bank will continue to exist. If you have a big bank that instead of 1,000 times that small loss has one bank having one major loss, probably the bank will default. Because from the moment they try to settle these losses, it will impact your market, and it will not be possible anymore. Yeah? It will move the market, so probably the bank is not just that trader will be fired, or maybe the manager will be fired. Probably the whole bank will collapse. It's a matter of scale. 100 times or multiple times a small loss is better than having one time a real big loss. What happens a few years ago with Société Générale, the trader Kerviel, that's an example of a matter of scale. If the loss that Kerviel had was spread out over several banks that simultaneously were saying, well, we have to settle this loss, probably it was not too bad. It was just that all these losses were comprised in one single bank, and that was impossible to settle with all the events afterwards, right? So it's a matter of scale, and that's what we show here. It depends on your dependence. It depends how your X and Y, or your X1, X2, X3 are moving together. If the more negative dependent they are, so the closer you are to that mutually exclusive case, the more linear they behave, where the scaling is not a problem. 100 times a small loss is the same as a big loss of 100 times the size. But if you have dependence, where things can occur simultaneously, where you can fall off 1 meter plus 1 meter plus 1 meter, and that 100 times, that will have a huge impact, right? Why is that? And you can make your plots to calculate the expected utilities. You make your concave plots. You see it's because you will crash in that very steep slope when you have big losses, right? You have a concave function, so the more you go to the negative side, the more severe you are punished. Again, your pain is outweighing your gain, which results in this type of inequalities. All right, I think I can and should end here. So if there are any questions, please do not hesitate to ask me a little bit after lecture, or send me an email. And otherwise, I hope that I see you back next week. Thank you.